Hey guys, today we will prove IMOC 2023 problem N5. Recall that we consider a prime P equal to 4k plus 1 and that we define x to be the smallest or the integer with smallest absolute value such that x is congruent to 2k over k modulo p. We want to prove that the absolute value of x is less than or equal to 2 times the square root of p. Most of this problem statement is not relevant for this chapter 2 because we have already dealt with interpreting x in chapter 1. Namely, we have defined n1 and now we define nr more generally as the number of pairs x, y in fp squared such that x to the power of 4 plus r equals y squared. And our main result from chapter 1 was that x is congruent to -1 minus n1 modulo p. Thus, our main task is understanding the value of n1. And to do that, we investigate the values of all the nr and the relationships between them. This is the content of the first half of the video where we will prove the following claims about nr. The first part is that the sum of the nr equals p squared. This follows from the fact that every pair x, y in fp squared is in exactly one of these sets, and therefore summing their quantities up yields exactly p squared. For our second part, we want to prove that the value of nr doesn't change when multiplying r by a non-zero fourth power. To prove this, we notice that x to the power of 4 plus r equals y squared if and only if qx all to the power of 4 plus q to the power of 4r equals q squared y all squared, which gives us the bijection x, y maps to qx, q squared y between the sets counted by nr and nq to the power of 4r. Next, we want to prove that n0 equals 2p minus 1. We can see that this is not a hard to count quantity because we just have to go through all of the quartic residues modulo p and see how many values for x and how many values for y we have that attain them. For the quartic residue 0, we only have one pair x, y equals 0, 0. For all non-zero quartic residues modulo p, of which there are p minus 1 divided by 4, we get 4 possible values for x and 2 values for y, so we multiply with 4 times 2 to obtain that n0 is indeed equal to 2p minus 1. The fourth part is proving that n1 plus ng squared plus ng cubed equals 4 times p minus 1, where g is some primitive root modulo p as in the previous chapter. We notice that we can partition fp into 5 sets, namely just the 0 and the set of fourth powers, the set of fourth powers multiplied by g and multiplied by g squared, and the set of fourth powers multiplied by g cubed. Moreover, the last 4 sets are of equal size, and therefore they must all have exactly p minus 1 over 4 elements. So, by the first part, p squared is equal to the sum of all the nr, which is by our partition, and the second part equal to n0 plus p minus 1 divided by 4 times the sum of I going from 0 to 3 of ng to the power of I. Using n0 equals 2p minus 1 and rearranging for this sum, we get our desired result. If we take a look at the fifth part, that tells us n1 plus ng squared equals 2p minus 1, and as well the fourth part, we see that in some way the expected value for ni with I not equal to 0 is p minus 1. This matches up nicely with our result from chapter 1, where we found out that x is equal to -1 minus n1 in fp, because -1 minus p minus 1 equals 0 in fp, and this is good because we want to prove that the absolute value of x is small. To prove 5, we notice that the set of non-zero quadratic residues modulo p is just the set of non-zero fourth powers plus the set of non-zero fourth powers multiplied with g squared. Therefore, p minus 1 divided by 4 times n1 plus ng squared is nothing but the sum of r and fp such that r is a non-zero square, so we write r is equal to z squared not equal to 0 of nr. This observation allows us to count the number of triples x, y, and z in fp cubed, such that we have x to the power of 4 plus z squared equals y squared, or x to the power of 4 equals y squared minus z squared, which equals y minus z, y plus z. To make top and bottom equal, we first have to add an n0 for z equals 0. Moreover, for each non-zero square r, there are two possible values for z, and so we have to multiply our sum with 2. And now, indeed, we have an equality. Since we have a bijection from fp squared to fp squared, mapping y and z to y minus z and y plus z for p greater than 2, we can rewrite this quantity in the following way. This is the number of triples x, a, b in fp cubed, such that x to the power of 4 equals ab. For x0, this equality is true if and only if at least one of a and b equals 0, and so we get a 2p minus 1. For all the other p minus 1 values of x to the power of 4 is also non-zero, and therefore we get exactly one possible value for b for each non-zero value for a. In other words, we get another p minus 1 squared. After subtracting n0, which is equal to 2p minus 1 from both sides, and then dividing by p minus 1 over 2, we get our desired result. The last idea is considering the sum of nr squared. We already found out that we expect a value of p minus 1 for n1, which is very good. Now we just want to prove that the error from this expected value is not too large. The sum is equal to the sum over r and fp of the number of quadruples x, y, u, v in fp to the power of 4 in such a way that we have x to the power of 4 minus y squared is equal to r, which should also be equal to u to the power of 4 minus v squared. Since we are summing over all possible values of r, we can just drop the sum and the r here. After rearranging the equality such that the second powers are on the right side, we can again change the y squared minus v squared into a product. Moreover, by summing over the possible values of x and u, we can simplify the counting. As before, we have 2p minus 1 possible values for a, b if the right side equals 0. For x is equal to 0, there's one possible value for u, namely 0. And for the remaining p minus 1 values for x, there are 4 values for u in every case. For the remaining pairs, x, u, this value is not equal to 0. And thus, again, we have p minus 1 possible values for a, b. So we get p minus 1 times p squared minus this value. My calculator says that this is equal to p cubed plus 3p squared minus 3p. Now that we know the value of the sum of nr squared, we can proceed as in the proof for claim 1.4, namely, we write this sum as n0 squared plus p minus 1 over 4 times the sum of I going from 0 to 3 of ng to the power of I squared. Since n0 squared is 4p squared minus 4p plus 1, we can rearrange this to obtain that this sum is equal to 4p squared plus 4. We define xi to be the difference between the expected value of ni, namely p minus 1, minus ni. By chapter 1, we obtain that x is congruent to x1 modulo p. The sum of ng to the power of I squared is now equal to the sum of p minus 1 minus xg to the power of I squared. Claim 1.4 tells us that the sum of I going from 0 to 3 of xg to the power of I is equal to 0. Hence, if we multiply out the right side, the mixed terms cancel out. By subtracting 4 times p minus 1 squared on both sides, we get 8p on the left, and on the right we obtain the sum of xg to the power of I squared. This is greater than or equal to x1 squared plus xg squared squared. And now we can finally use claim 1.5, which tells us that x1 plus xg squared is equal to 0. In other words, this sum is equal to 2 times x1 squared, and after dividing by 2 and taking the square root on both sides, we obtain that the absolute value of x1 is less than or equal to 2 times the square root of p. Since x and x1 are congruent modulo p, and x has a minimal absolute value with that property, we know that this is greater than or equal to the absolute value of x, which finishes our proof.